So what I want to do now is put together what we've talked about so far as statistical techniques, correlation, regression, z-test, and z-test for single samples. So we're going to talk a little bit about what the mathematical formulas are estimating broadly across all of these, but we'll also talk specifically about how we report, what we get out, and how to interpret these various inferential tests. And again, a reminder that inferential simply means that we're inferring from our sample to a larger population. And statistical significance is the probability that we can make that inference. How likely is it that we're correct that what we found in our sample would also be found in our population? A good idea to remember also is that the formulas, in other words, the mathematics that we use, have no idea what is going on. They are not aware. They don't know if we have good data, bad data. They don't know if our assumptions have been met. They don't know. For example, you could put in any number into the equation for the z-test for single samples, including an n of less than 30. And you'd get a result, and you might even get a significant result, but you violated the assumptions. It's one of the reasons that the assumptions of each test are important. They are things that we need to check as researchers so that when someone reads a statistical test that we're presenting, that we got a critical value, we calculated the test and got a value, and we've calculated whether or not it's significant or not, let alone how important or the size of the effect size, that actually is meaningful, that we've done our due diligence to make sure that we're using the right test, we've met all the assumptions, and that it is a rigorous use of that test. In other words, we know about the quality of the data that's going in. The mathematical equations do not. So let's just briefly review for correlations, the statistical significance of R, which is the test statistic, indicates whether R differs from 0 and how likely that difference is due to chance rather than due to a systematic relationship. So what R is looking for is simply, is there a meaningful pattern? Is there a relationship? So when we get a value of R, it tells us how strong that relationship is. And our statistical significance tells us whether or not that is due to systematic differences that we'd be likely to find in other samples, or is small enough that it could just very well be random noise. Generally, when we're looking at correlations, we're comparing two continuous variables looking for a pattern. And when interpreting the correlation, we want to consider whether it's statistically significant. We want to determine the direction of the relationship. We need to know how the variables were coded for this. And we need to know the strength of the association, the size of the effect. And for correlation, the effect size is R squared. So our calculated statistic is also squared, becomes our measure of effect size. So how would we report this is we'd report R italicized, parentheses, our degrees of freedom. So remember, that does tell us the size of our sample, but it is not often the sample itself. It usually is adjusted with a negative, so for example, -1 or -2. We have the actual calculated value, 0.50. We have the fact that the p-value is below or less than 0.05, so it is statistically significant. And because of that, we're going to report the effect size, also italicized, R squared, which is 0.5 times 0.5 or 0.25. In other words, the relationship between these two variables explains about 25% of what's going on. That means 75% is unexplained. Other variables are affecting it that we haven't measured. But what this basically calculates is that we believe that we have evidence that there is a relationship. We have the direction of the relationship based on the two variables and how they're coded, and that relationship is explained about 25% of what's going on. With simple linear regression, we're adding on top of correlation. We're still looking at two continuous variables. However, in this case, we're actually predicting a continuous variable from another. So the results of regression analysis indicate how accurately the independent variable, in other words, the predictor, can be used to predict the DV or the outcome. Again, we will get an R and an R squared, but we usually report this as an italicized large beta to represent the fact it was a regression and not a correlation. And again, the value, the B, is how much change in the DV, the outcome, occurs when there's a 1-unit change in the IV, or predictor. And this is beta, or just a capitalized B italicized. So this is actually dependent on the scales used. The Latin beta B is actually standardized. It is our test statistic. But beta B, using just Arabic numerals, large B, that represents actually the value that changes with a 1-unit change in our predicted outcome. So what score on the DV corresponds with a 0 score on the IV? That's our y-intercept. And having our y-intercept, our beta, and our b allows us to actually determine what's going on. This information can then be used to predict a DV score from an IV score. So later, once we have this, so we conduct a study where we have both the predictor and the outcome. We grab that sample, we find this relationship, we find it statistically significant. From that point, we're now going to infer. We're going to infer that in the future, if we have someone's predictor score, we can predict how their outcome would be. And this is actually the basis for a lot of selection and determination. So basically, when you apply to a college or a grad school, they'll look at your previous GPA and potentially your score on an SAT or GRE to determine how well they think you'll do in the university, whether it is an undergrad or graduate degree. And so what they're doing is they're doing prediction. They're basically predicting based on your previous GPA, what would we expect your GPA now to be, and is it acceptable? And that's generally how selection in academia occurs. We also will see this throughout many organizations who will give employment tests to use those tests to make prediction on how well of a performer you are. And this is again based on previous studies which actually sampled people, gave them the predictor test, and then actually looked at what was being predicted, the outcome, performance. And they found a relationship, a significant relationship, allowing them to then use this equation. So how we'd usually report this is we report B so that someone actually knows what the actual value in the scale is. We'd report that Latin beta, which is the actual test statistic. And then we generally report actually a t-test to determine if that's significant. And then the p-value. So this is again how we would report a simple regression compared to how we would report, for example, a correlation. We also discussed the Z or standardized scores. It is generally non-inferential, so we don't calculate a p-value. It asks applied questions. So we're not necessarily trying to infer to larger samples. We're just trying to compare people's scores. Compares individual scores on two continuous variables, and the independent of the original measurement scale and sample size allows us to look at pretty much any two scores as long as we actually have the person's score on that test, the mean of people on average that take that test, and the standard deviation of people on average that take that test. And this could be a large population or it could be a sample. So for example, if I'm wanting to look at someone's Z-score on a test, I would need to know the mean of everyone who took that test and the standard deviation of everyone that took that test. That might be a small sample. It might be 22 students. But again, this allows us to calculate a Z-score to get an idea of how that score would reflect if we compared it to other scores, other people, other classes, or even other measures of the same construct. And finally, we talked about the Z-test for single samples, which is an inferential test using kind of the same concepts as the Z-score. The Z-test is an inferential statistic comparing a single sample mean on a continuous variable to a population mean on the same continuous variable when the variance is known, mean and standard deviation. So when interpreting a test statistic, always we want to consider the statistical significance, the p-value, the direction of the difference, which scored higher. Inferential test does not use DF values set for the Z-score. And what that means is that the Z-score is the only inferential test that does not actually use sample size to determine whether or not there is significance. In the case of the Z-score, it is simply a set critical value, which we've discussed in previous lectures. How you report this is simply Z, again italicized, the actual value, and whether or not it's significant. So just as a reminder, even though the Z-score, and we have the Z-test down there, one tail and two tail, the set values, always, whenever we're looking at inferential statistics, there is some process where we're comparing the obtained test statistic, so the R, the beta, the Z, to a test statistic probability distribution that has already been determined, and then we compare that to a critical test statistic. For Z-tests, it's a set value because the sample size has already been adjusted for in the equation. But when we look at correlation, for instance, it is dependent on the actual degrees of freedom or the number of people in our sample, depending on the table you look at. So in this case, remember correlation, the degrees of freedom is the n of the sample minus 2. So if I had 9 people in my sample, 9 minus 2 is 7. I would find the 7 on this table, and if I'm looking for a p-value of 0.05 or smaller, it gives me that critical value of 0.66, and I'm going to round it up to 7, so 0.667. That is what I would need to have that value or higher in order to claim statistical significance. So as we move forward in this class, what we're now doing is we're actually looking at various statistical techniques and we're adding those statistical tools to our toolkit. We're learning how to use regression, we're learning how to use simple regression, and correlation, simple regression, and we're looking at the z-score and z-tests. These are what we're actually adding to our toolbox at this point. What we're now going to do, having this basis in methodology, understanding why we're doing these things and the importance of the assumptions, we're going to start adding more techniques to this toolkit.